Hi, welcome to TemurTube. In today's video, I want to show you how you can use the kiwi3d Grasshopper plugin to analyze structural systems. Kiwi3d is a free Grasshopper plugin designed for educational and research purposes. I will be modeling the Warren truss that you see in the picture. At the top, it has n members, and at the bottom it has n+1 members. We will assume that all horizontal members have the same length w, and the height of the truss is h. The top members have an offset of w/2 to the right and left on both sides. First, let us define the parameters in Grasshopper. We will define 3 parameters and construct the truss from them. Number of members at the top. Total length of the top chord. Truss height. First, let us construct the bottom chord. We will start at the coordinate 0, 0. To find the second point, we first calculate the length of one member by dividing the length of the top chord by the number of members, and then add this value to the length of the top chord. This gives us the x-coordinate of the second point. Then we construct a line between these 2 points. For the top chord, we use a z-value equal to the truss height, and we set the start point at half of one member length. The second point can be found by adding the length of the top chord to the x-value of the first point. Then we construct a line between these 2 points. Now let us divide the bottom chord and the top chord by the number of members at the bottom and top respectively. This will give us the points needed to construct our diagonals. The bottom chord has one extra point, so we will split the list of bottom chord points and match the number of points to the top chord. Then we use these points to construct the diagonals. For the other set of diagonals, we will do the same process, but this time we remove the first point. After getting the diagonals, we need to have the top and bottom chords separated. For that, we use the shatter command and split the lines. We use the t values from the divided curves to shatter the curves. Now we have each individual member of the truss. Next, let us extract the support points from the bottom chord. We need the first and last points. For the first point, we use index 0. For the last point, we determine the list length and subtract 1. Now we have our truss fully parametrized. When we change any of the 3 parameters, and the truss adjusts automatically. Now let us move to kiwi3d. First, let us create the material. We will assume our truss is made of wood. We need to define the name, material type, Young's modulus, Poisson's ratio, density, and yield strength. For the material type, we will use a value list. Next, we define our cross-sections. For the top and bottom members, we will use rectangular cross-sections. We need to define the width and height. Now let us define our top and bottom members using the beam component. For the curve input, we provide our curves. For material and section, we use the material and section we defined earlier. We also need to define curve refinement for the integration points. Let us define the diagonals in the same way. We will use circular cross-sections for the diagonals and define the diameter. We then create our diagonal beams using the same method. Now let us define the load. We will define point loads. We need to specify the points, so we will use the nodes of the top members. To define the load type, we use a value list and select from the available load types. For the direction, we use the z vector and reverse it since the load acts downward. We also need to give a load value, so we will use a number slider. Finally, we define a load case. Now we are done with our finite element model. The next step is analysis. For that, we use the analysis model component. We need to specify the analysis type. Let us define a linear analysis. Let us connect our beam elements to the E input. Now we need to connect the supports. We have not defined them yet, so let us define them. We will define point supports. We need to provide the support points and fix the X, Y, and Z directions. We can also fix the rotations for now. Let us join the supports to our analysis model. Now we connect our loads as well. For controlling visualization and scale, we can connect the Visualize Options component. Now we use the IGA solver to solve the model. Let us connect our model. To run the model, we need a Boolean toggle. We have an error. This is because our inputs need to be flattened. Let us flatten them. Let us also add a value list to control the output type of our results. Now we can run the simulation by clicking the toggle. You will see a black screen while the model runs. Now let us look at the deformed model. We need the deformed model component. Connect our model and a number slider to control the scale. Let us turn off the visualization for better visibility. Let us also increase the scale. Now we can see the deformed shape clearly. Next, let us look at the member forces. For that, we need the 1D element result view. Let us connect our model and a value list to select the result type. Let us adjust the scale. Let us control the end conditions of the members. We can switch between truss and beam elements by releasing or fixing the node rotations. By toggling the buttons, we can switch the end conditions. When the rotation is released, there is no member moment. Let us also release the rotation at the supports. We can also take a look at the support reactions. Now let us look at the utilization of the cross sections. As you can see, the utilization is very low. We can increase the load and check it again. Now the utilization has increased. Using our parametric model, we can change our parameters and perform our design. I hope this tool helps you a lot in dimensioning your structures, at least in the preliminary phase of design. Thanks for watching. If you find the content useful, don't forget to like and subscribe to our channel. It helps us create more content like this.